Hello Internet, I want to start by giving you my answer to Johnny's answer to Arcadia, which is rural Lincolnshire. Where exactly? Well, I'm not telling you, but if Jesse's taught us anything already, it's that you could probably find out from Facebook. Lincolnshire is a place where people can count their sorrows on one hand, so the maximum amount of sorrows someone can have is 7.
Anyway, my name's Tom, I'm from the botnet, and I was one of the first people born into a world where Fermat's last theorem wasn't a mystery. So last month I teased you by saying that everything in maths was connected, and that the greatest proof in the last 20 years was just a proof of a connection between two different fields of maths, called elliptic equations and modular forms, first suggested in something called Taniyama-Shimura conjecture. This could be used to prove a piece of 300-year-old maths called Fermat's last theorem.
Okay, let's steal Hart's format for a minute. Fermat's last theorem looks a bit like Pythagoras' theorem, where in a right-angled triangle, a squared plus b squared equals c squared, and there are examples in Pythagoras' theorem where a, b, and c are all whole numbers, and they're shown here. Fermat's last theorem says that if you cube the numbers instead, or raise them to any other power higher than 2, then a, b, and c can never be whole numbers.
It's called Fermat's last theorem because in the 17th century, a mathematician called Pierre scribbled it in the margin of a textbook, along with the phrase, "I have discovered a truly marvellous proof of this, which this margin is too narrow to contain." This teased mathematicians for hundreds of years until real progress was made in proving the theory in 1957, when Japanese mathematicians Yutaka Taniyama and Goro Shimura proposed a conjecture which linked two very different areas of maths.
Elliptic equations were just equations which you could draw on a graph and had this form where a, b, and c were just any numbers you'd like. If you changed a, b, or c, then you got a different elliptic equation. The challenge with these was finding whole number solutions, that is, solutions where y and x were both whole numbers, and in particular finding out how many whole number solutions each elliptic equation had. Now with a normal number line going 1, 2, 3, 4, 5, 6, and so on, finding the number of whole number solutions in an elliptic equation was impossible, but it wasn't when you consider special circular number lines where you count 1, 2, 3, 4, 5, 1, 2, 3, and so on, round in a circle. This special type of counting is known as clock arithmetic because we use it when we count hours in the day. 11 o'clock, 12 o'clock, 1 o'clock, and so on.
It's also called modular arithmetic, but since I'm going to come on to modular forms in a minute which have nothing to do with modular arithmetic, I'm going to call it clock arithmetic to avoid confusion.
You can add, multiply, and subtract in clock arithmetic, although dividing is a bit more tricky, and it was possible to work out how many whole number solutions any elliptic equation had on a number clock, if not a number line. Of course, the number of solutions depended on the size of the clock, so what you got was a list of the number of solutions for each clock. Each list, called the E series, was unique for each elliptic equation. Essentially, it was its DNA.
Modular forms are terrifyingly complicated, so I won't say much about them, apart from the fact that they are four-dimensional objects which have an infinite degree of symmetry. You can twist them, or shift them, or grow them, and they will look the same as before. Well, I say look. They're impossible to actually visualise, which, you know, helps.
The interesting thing was that modular forms seemed to also have a list of whole numbers called the M series, which made up their mathematical DNA, and every M series seemed to have an elliptic equation E series counterpart where the two DNA sequences always matched up. Taniyama and Shimura thought this was always true, but they couldn't prove it. From this, Gerhard Frey and Ken Ribbett proved that you could turn the contradiction of Fermat's last theorem into an elliptic equation, and that this elliptic equation's E series did not match up to the M series of any modular equation. This meant that either Fermat's last theorem was wrong, disproving Taniyama-Shimura, or if Taniyama-Shimura was proved right, then Fermat's theorem would be proved right.
This, finally, is where Andrew Wiles comes in. He first read about Fermat's last theorem at the age of 10 and became obsessed by it. In 1986 to 1993, he did nothing but work on proving Taniyama-Shimura in order to prove Fermat, and then he did the same thing a year after that because of a mistake that he'd made, before finally publishing in May 1995, a month before my birthday. He used an enormous amount of maths from the 20th century in order to prove this connection, and the reason I'm not explaining any of it to you is because I don't understand it. Andrew Wiles, an Englishman by the way, is now Sir Andrew Wiles and remains one of the greatest living mathematicians today. Internet, I'm Tom, this is the Botnet. Like us, favourite us, tweet us, Facebook us, goodbye! By the way, I forgot to mention that all the material in this video was stolen from Simon Singh.